Hello, welcome to Curated. Today we will be discussing a problem which is known to be asked in companies like LinkedIn, Amazon, Google, Bloomberg, and Microsoft based on interview reports. The problem statement goes like this: you are asked to design a stack that supports all the usual operations such as push, pop, top, but also supports two additional operations: peekMax and popMax. peekMax returns the maximum element from the stack, whereas popMax removes the maximum element from the stack. Note that popMax should remove the topmost occurrence if there are duplicates. Let me try to explain this with an example. Say you have a stack, and let's go over a set of operations as an example. Let push of 5 be the first operation. So we push 5 into the stack. The next operation, push of 1, we push 1 into the stack. The next operation, push of 5, we push 5 into the stack. The next operation is top. We get the top of the stack, that is 5. So the answer for this is 5. The next operation is pop max. We need to pop the maximum element from the stack. There are two maximum elements in the stack, it is 5. But we need to pop the topmost element, that is the first 5. Let's pop it. Next operation is again top. Top of the stack is 1, so the answer is 1. Next operation is peak max. The max element in the stack is 5, and the answer for peak max will be 5. The next operation is pop. So we pop the top of the stack, that is 1. I hope the example was clear. Basically, we need a stack that behaves normally but also knows how to remove the maximum element correctly. What is the easiest way to solve this? It's actually very simple. Just use a normal stack and do all the operations. So the pop operation will be of time complexity big O of 1. The top operation will be of time complexity big O of 1. The push operation will also be of time complexity big O of 1. What about peak max? To find peak max, you need to traverse the entire stack and find the maximum value in the stack. Say the maximum value is initialized to maximum integer value. And then you iterate over the entire stack. Say the stack is stack variable, and then update the max as you traverse over the stack. So this will give you the maximum element in the stack, which would be the peak max. The time complexity would be big O of n because we traverse over the stack. What about pop max operation? You need to first find the maximum element in the stack and then remove the topmost occurrence of that maximum element. To find the maximum element, we call the peak max operation as the first step, and as the second step, we keep popping elements from the stack until we find max. Let's take an example. Let's say you have 2, 5, 8 and 6. So the maximum element in the stack is 8, right? So peak max gives you 8. And now you need to keep popping the elements from the stack till you arrive at 8. That is, you need to store those popped elements into a temporary stack. Okay, so first you pop 2 and then you pop 5 and then you arrive at 8. So you pop it from this stack and then you push back the elements from the temporary stack to the original stack. So first you push back 5 and then you push back 2. We popped the maximum element from the stack, and every time we call popMax, we are basically touching almost every element and rebuilding the stack. So that makes it big of n time complexity, which is too slow if we do it repeatedly. So the real problem is we don't have a fast access to the max. Actually, peekMax can be improved by using a heap. So instead of big O of n, it will be big O of log n. But the second step of removing the max from the stack would still take big O of n, which is too slow for this problem. How should we go about thinking this? This problem is actually asking for two different abilities. It is asking for stack behavior, that is last in first out. It is also asking for fast maximum element tracking. A single data structure is bad at doing both. We used stack and we saw that stack was great for order, but it was very bad at tracking max. Let's first fix tracking max. We need sorted data for that. Think which data structure can be used. We already saw that heap does not help. So think about which data structure we can use. The sorted data structure that we will be using will be TreeMap. You will get to know why TreeMap. TreeMap sorts the keys in ascending order. So an example of TreeMap looks something like this. The smallest key has the first key and the largest key will be at the end. Now I can get the max element instantly using the last key function. But I only know the value of max. I still don't know where it is in the stack. For popMax operation, to delete any element efficiently, I need direct access to it because we already noticed that iteration was bad. So think of which data structure gives us access to element in big O of 1. Not stack, not array, because there you need to traverse the whole data structure, right? So which data structure we need to use? It is linked list, right? Using linked list, I can remove any element in big O of 1, even if the element is in the middle. Here we will be using a doubly linked list and you will know why. DLL will have nodes with every node connected on both sides. So every element exists in two places, in the tree map for max tracking and in the DLL which acts as a stack. How do I connect both these places? Doubly linked list has nodes connected via links and each node has a value of type integer, a next node and a previous node. So to connect tree map and the doubly linked list, we store the corresponding node for each key in the tree map as its value. What if there are duplicates in the stack? Let's say there are two sevens in the stack. So we will have two different nodes for each of them, right? Say the node for the first 7 is node 1 and the node for the second 7 is node 2. In the tree map, for the key with value 7, we store the list of node 1 and node 2 as the value. And we also know that each node object contains the value, here it is 7, and the link to the previous node and the next node, right? So TreeMap is a map of element to the list of nodes. During the popMax operation, if the max appears more than once, then you need to remove the topmost one from the stack, that is the most recent one from the stack. So you will be removing the last node in the list, which would be the most recent one. And the same node would be removed from the doubly linked list from wherever it is present. Anyways, the operation will always take big O of 1 to remove it from any place. Say you want to remove 7, cut the link with 1, cut the link with 5, and then rejoin the links of 1 and 5. It's just big O of 1. So next, let us do a dry run on an example and also try to calculate the time complexity for every stack operation. Let us go over the dry run using the following operations as an example. As we discussed, we will be using a doubly linked list which acts as a stack. We use head and tail as dummy nodes in the linked list because it helps us in simplifying the operations. So the first operation is push of 5. We create a node using 5 and add it to the doubly linked list. So whenever we add a new node to the doubly linked list, we add it either before the tail or after the head so that an order is maintained for the recently added element to the stack, which helps us in operations like pop and top. Here in this example, let's go with adding the recent element just before the tail. Hence, we add the node with element 5 just before the tail. This is the doubly linked list. We also need to add the element to the tree map, which is a map of element to the list of nodes. So we add the element 5 to the map and the node of 5 to its list. The next operation is push of 1. We create a node with value 1 and add it to the doubly linked list just before the tail. We add 1 to the map and the node of 1 to its list. The next operation is push of 5. Create a node with value 5 and add it to the doubly linked list just before the tail. To differentiate between these two nodes with 5, let's call this node as 5a and let's call this node as 5b. So this will also be 5a. Also add the new node 5b to the list. The next operation is push of 3. Create a node with element 3 and add it to the doubly linked list just before the tail. We add the element 3 to the map and the node of 3 to its list. The keys will be sorted in the increasing order in the tree map. The next operation is push of 5. Create a node with element 5 and add it to the doubly linked list just before tail. Let's call this node 5c. The key 5 is already present in the map, so we add the node 5c to the existing list. The next operation is top. The topmost element is the one which is just before the tail, which is the node 5c, and its value is 5. So the answer for top is 5. The next operation is peekMax, that is the maximum element in the stack, which is nothing but the last key in the tree map, which is 5. So the answer for peekMax is 5. The next operation is popMax, that is remove the maximum element from the stack, which is the last key of the tree map, that is 5, and 5 has 3 nodes in the list, which means there are 3 5s in the stack and you are supposed to remove the topmost 5. Remove the last node from the list which contains the topmost 5 in the stack among all these. Also remove the node from doubly linked list. Let me also write the head here so that it looks clean. The popped value for popMax would be 5. We return 5 from the method. The next operation is top, which is the value in the node just before the tail, which is 3. So we return 3. The next operation is peekMax, which is nothing but the last key in the map, which is 5. So we return 5. The next operation is pop, that is pop the topmost element from the stack, which is the element in the doubly linked list just before the tail. So we remove it from the doubly linked list. At the same time in the tree map, remove the node 3 from the list for the key 3. And we see that the key 3 has an empty list. So remove the key 3 from the tree map. And we return 3 for this pop operation. The next operation is popMax, that is remove the maximum element from the stack, which is the last key of the tree map, that is 5. 5 has two nodes 5a and 5b, meaning there are two 5s in the stack, and you need to remove the topmost 5 from the stack, which is nothing but the last node in the list, which is 5b. Also remove it from the doubly linked list. At the end we return 5 for the popMax operation. We covered all the operations in the example. What is the time complexity for push operation? We insert into the doubly linked list, which is big O of 1 plus inserting into the tree map, which is big O of login. So the overall time complexity big O of login. For the top operation, we access the element just before the tail to get the topmost element in the stack. So it is big O of 1 time complexity. For the pop operation, we pop the node from the doubly linked list, which is big O of 1, and we also pop the node from the tree map, which is big O of login. So the overall time complexity is big O of login. For the peekMax operation, we get the maximum element in the stack by accessing the last key in the tree map. So the time complexity is big O of login. For the popMax operation, we pop the maximum elements node from the tree map, which is big O of login. We also pop it from the doubly linked list, which is big O of 1. So the overall time complexity is big O of login. What is the space complexity? The doubly linked list stores n nodes, so it will take big O of n space. And the tree map stores unique keys with references to the nodes, right? So in the worst case, if there are no duplicates, the space it takes would be big O of n. So the overall space complexity will be big O of n. I hope the dry run was clear. Let us go through the code. As the code is long, I'll just be walking through it. The problem guarantees that all operations like pop, top, peekMax and popMax will only be called when the stack is non-empty. So we don't need to handle empty stack edge cases in our implementation. Let's go through the max stack class implementation. As discussed, we will need a doubly linked list and a tree map. For doubly linked list, we declare a class DLL node with value of type integer, a next node and a previous node. DLL node represents each node in a doubly linked list. So in the max stack class, we declare head and tail for the linked list to simplify operations and a tree map of integer and list of nodes. In the constructor, initialize head, tail, point heads next to tail and tails previous to head, and also initialize the tree map. Let's check the push method. The integer to push is x. We create a new node with integer x and then we check if x exists in the tree map. If yes, get the list of nodes, else create an empty list of nodes and add the newly created node to the list and update the map. We have added the node to the tree map. Now we add it to the doubly linked list by calling the add node method. Add node method adds the node to the doubly linked list just before the tail using the previous and next links. And the overall time complexity is big O of login. Let's check the pop operation. We are supposed to remove the topmost element from the stack which is present in the node just before the tail. So get it and get its value and remove the node from the doubly linked list by calling the remove node method. You can check this out. From the tree map, get the list of nodes for that value and remove the last node from that list. And if the list becomes empty, remove that key from the tree map and at the end return the value of the removed node. The time complexity is big O of log n. The next operation is top, which is the topmost element in the stack, that is the value in the node just before the tail, with the time complexity big O of 1. The next operation is peekMax, which is the maximum element in the stack, that is the last key of the tree map, which amounts to big O of log n. The next operation is popMax, that is remove the maximum element from the stack. First get the maximum element, which is the last key in the tree map. Get the corresponding list of nodes for that value in the map. Get the last node from that list. Remove the last node from the list. If the list becomes empty, remove that value from the map. Also remove the node from the linked list and at the end return the value of the removed node. And the time complexity is big O of log n. Let's try running the code on the example input. And we got the expected output. If this made it clear, like and subscribe for more such videos. Thank you.